In this tutorial, we're going to be looking at finding the inverse of functions. We're going to start off simply with linear functions and then head towards quadratics. Now, the quadratics bit only really applies to the i-GCSE syllabus. It's not contained in the ordinary GCSE, so you could turn off at that point if you wish. Let's have a look. Well, I've got 3 questions here, starting off with linear functions and then ending up with quadratics as I promised. Let's do them one by one. I think a function is most usefully thought of as a box, which if you put x into its input, you will get the function's rule out. In this case, we will double every input value. It will be doubled on the output. So we will get 2x on its output. When we talk about an inverse, what we're asking is, well, look, if we've got this function box here, which is transforming x and doubling it, what would happen if we put x into effectively the wrong side, into the output? What would we get out here? I think you wouldn't be surprised to find out that if we put x into a box which multiplies by 2, put it in the wrong way, we would get x over 2 here. But how would we work that out in a method that would apply when the functions are more complex, as in b and c? To find the inverse, we temporarily bring back our old friend y. We say let y equal 2x. And what we do is we make x the subject. So writing it just the reverse way round, we get 2x equals y. And therefore, if I divide through by 2, I will get x is equal to y over 2. Now we swap x for y and y for x. And we get y is equal to x over 2. And that, because we've swapped the x's and y's round, that is the inverse function and the answer to part A. So let's now apply the same technique to part B. We say let y equal 6x minus 5. And we need to make x the subject. Writing this the other way round, 6x minus 5 is equal to y. Therefore, moving the 5 across, it becomes positive. We get 6x is equal to y plus 5. And therefore, now dividing through by 6, x is equal to y plus 5 divided by 6. Now we make our swap and we get that y is equal to x plus 5 divided by 6. And this is f to the minus 1x. That's the notation that we use for the inverse function. fx, when we find the inverse, is transformed to f to the minus 1 of x. And that's the answer to part B. Part C done in exactly the same way. Let y equal 2x plus 4 divided by 5. Therefore, cross-multiplying, 5y is equal to 2x plus 4. X now has to be the subject again, so we get 2x is equal to 5y minus 4, and therefore x is equal to 5y minus 4, all divided by 2. Now our swap, and we get f to the minus 1 of x is equal to 5x minus 4, all divided by 2. And that's the answer to part C. But just before we move on to harder examples of finding inverse functions, just let's have a look at what we've created so far. 2x is plotted as the red line, and what we found, x divided by 2, is plotted as the green line. And that's true for both part B and part C. Here's 2x plus 4 divided by 5. Look at the 3 inverses. They're plotted in green. The crucial fact to remember is that they are all reflections on the line y equals x. It can be held up as a mirror to the red line to create the green line in all 3 cases. And that's going to be true of every single inverse function we create. It will be a reflection on the line y equals x. So this is really where GCSE students should leave the tutorial. This is as much as your course will require of you. i-GCSE students should stay with as we move on to finding the inverse of quadratic functions. Okay, let's have a look at this one. Let's have a look at 2 part A. And we'll try our same method. We need to make x the subject, so therefore we can say x squared is equal to y minus 6. And therefore x is equal to the square root of y minus 6. But we've got a problem. When we take a square root, it's not just the positive result, it is the negative result as well. Now that is going to cause us a problem, and I'll explain that in a moment, but for the moment, that is the answer, that f to the minus 1 of x will be equal to plus or minus the square root of x minus 6. And that's the answer for part A. Okay, let's try part B. To solve this, we need to take the square root of both sides, and when we take the square root of y, we've got to remember plus or minus. So therefore, plus or minus the square root of y must equal x plus 8. So moving things round, x is equal to plus or minus the square root of y minus 8. So therefore, f to the minus 1 of x is equal to plus or minus the square root of x minus 8. And that's the answer to part B. Now I said this plus or minus is going to cause us grief. Let me explain that. So on these 2 plots here, we've got the original curves x squared plus 6 and part B's curve here, x squared plus 8, all squared. The green lines again plot the inverse. And once again, yes, they are the reflection in the line y equals x. But the problem is that both green lines aren't strictly, in mathematical terms, functions. And the reason is, if I put a vertical line through both of the plots anywhere I like, I will get 2 answers for the vertical value. This answer here and this answer here. Equally, on part B's version, yes, I get 2 more vertical values. And the strict definition of a function is that we cannot have 2 vertical values. This is a function because as I go along from left to right, I only have 1 vertical value for different values of x. So fx is a function, but f to the minus 1x is not a function. Well, what's the cure? Well, the cure is to restrict the domain, in other words, the x values of our original function. If I only allow this curve to come up from its minimum point upwards, I will cut off half of the inverse. Similarly, this curve, if I only allow the positive section, in other words, from x equals negative 8 upwards, I will cut off half of this curve. Let me show you those diagrams. And here they are. As you can see, every value of x that I apply to our original function below 1 is now not allowed. So the function starts from its minimum point and heads upwards. So my restriction for this curve is x is greater than or equal to 0. Because I've chopped the left-hand side off, we've only got 1 branch of the inverse. And happily now, we only have 1 y value as x increases. This now can be called a function. And similarly, over here, we're only allowing values of x greater than or equal to negative 8. And yet again, because we've only got 1 value of y for every value of x on our inverse function, this is mathematically a function. Okay, let's have a look at part 3. we bring back y and make y equal to the function. Now, I want to make x the subject. Okay, I can push the 15 across, so we get y minus 15 is equal to x squared plus 6x. I can probably take an x out of this, but I'm really stuck. I can't make x on its own the subject of the equation. But there's a technique we can use that can make x the subject. Let me show you. And it's our old friend completing the square. To complete the square, I can form a bracket of this coefficient halved plus 3. Now I'm going to write the plus 15 over here because we need to do a little bit of side work. We need to find out what this guy on its own actually produces. We get x plus 3 multiplied by x plus 3. Well, our first multiplication, x times x, does give us x squared. And the underneaths, 3x and another 3x gives us 6x. But this multiplication of 3 times 3 is unwanted. 3 times 3 is 9, so this will give us a positive 9 that we don't want. So I need to take away that 9 straight away to balance everything back up again. Pushing the negative 9 and the 15 together, we get y is equal to x plus 3 all squared plus 6. Now let's try to make x the subject with this arrangement. I can say x plus 3 squared is equal to y, which was on the left-hand side but now the right, and the 6 has moved side, so this is negative 6. Well, now I can take the square root of both sides, and I get x plus 3 is equal to the square root of y minus 6. But again, we have to remember, when we take a square root, we have to include plus or minus. Most of the time in geometry, we can get rid of that minus because we're dealing with positive dimensions. But with these functions, we can't. So what have I got now? I've got x is equal to negative 3 plus or minus the square root of y minus 6. Now we have got x the subject of the equation. So now we can swap x for y and y for x. And because we've got the inverse function, we can now say that this is therefore equal to f to the minus 1 of x is equal to negative 3 plus or minus the square root of x minus 6. And that is your answer. And just to show you what this all looks like on a graph, here's our original quadratic, as you'd expect, a U-shaped quadratic, and here is the inverse. And yet again, it is the reflection on the line y equals x. But to mention again, we can't call this inverse of the quadratic equation a function, because if I pop a vertical line across the function at any point, I get two answers for y. So to avoid this problem, we have to restrict the domain of our x values such that we only have half of this curve. Things would look like this. For this case, we would have to restrict the domain of x so that it didn't go below negative 3. This would mean our inverse function doesn't go below negative 3 in y terms. Now we're okay. We can truly say that this inverse is a function because there is only one y value for increasing values of x. One more interesting point here is that our master curve in this case is plus or minus the square root of x, and our inverse here demonstrates very well transformations of curves. First of all, look what we've done to x. We've taken 6 away from x here, which means the graph shifts to the right by 6. Remember, that's the big elephant trap when you deal with horizontal changes. This negative 3 is slightly easier to deal with. It just pulls the graph down by 3. So I think that's a really good example of the transformation of curves. Let's go on to part B. I'll leave this all here for the moment so that you can see the comparison. Now, one of the restrictions of completing the square is that we have to have this x squared term effectively without a coefficient. So I must take a factor of 2 out of both of these terms and rewrite. Now we can complete the square of the bracket, keeping the factor of 2 outside. So we get 2. Because we've got a coefficient of 12 here, our completed square bracket will be x plus 6 squared. So again, let's do a little bit of side work on the multiplication out of x plus 6 and find out effectively what error it produces. We'll generate two terms that we want, which is the x squared, and if we look at the underneath, this is 6x, this is 6x, so we get our plus 12x. That's all good because we want these two terms. But what we don't want is 6 times 6. So we need to take away 36 from our multiplication here, such that we put the book straight. So negative 36 goes in here, and we close this bracket, and then minus 3. Okay, let's lose this bit of side work now and continue on. We're splitting this bracket apart. The 2 will multiply both our bracket term and the 36. And therefore, y is equal to 2 times our bracket, which is 2x plus 6 squared, minus 72, and then bringing up the rear, minus 3, which is equal to 2x plus 6 squared minus 75. Well, now we can start the process of making x the subject. So therefore I can say x plus 6 squared is equal to y plus 75. The 75 moves sides and becomes positive, divided by 2. Now we take the square root. Therefore, x plus 6 is equal to the square root of y plus 75 over 2, not forgetting our plus or minus out the front here. And now I can introduce the inverse function routine. F to the minus 1 of x is equal to negative 6 plus or minus the square root of x plus 75, both over 2. And that is your answer to part B. And just to finish off, here is the plot of what's been going on. Here's our original function, and the green line is the inverse. Yet again, you can see it is the reflection in the line y equals x. Let me say that the green line is not a function until we restrict the domain of our original function. I hope that made sense.